and welcome. Today we are going to be talking about some probabilities and specifically probabilities of multiple events. So two events A and B are said to be independent if the probability of B occurring is the same whether A occurs or not. In other words, A has no effect on B. The outcome of event A changes the probability of B. If that happens, then they're dependent events. So let's take a look at a few examples and make sure we can clarify what that means. You roll two dice and want them both to land on a 6. Well, does the first die affect the other die? Like if you roll the first die and it lands on a 6, does that change if the second die? Does it affect it in any way? No, it doesn't. These are going to be independent events because one die does not affect the other. A fair coin is tossed 2 times, and you want the coin to land on tails or tails the first time and then heads. So when the when the coin lands on tails the first time, does it affect whether or not it will land on heads? No. These are independent events as well. Knowing that the coin landed on tails the first time has no effect if it lands on heads the second time. Some people will even say the coin has no memory. Right? It doesn't remember what it did last time, so it can't affect what it's going to do next time. Two cards are selected from a standard deck of cards without replacement, and you're hoping that one of them is the ace of spades. So when you draw a card the first time and you look at it and you see that it's the king of spades, when you go to draw a card the second time, the likelihood that that next one is an ace is actually just a little bit higher because there's one less card in the deck. There were 52 cards. You had a 1 in 52 chance of drawing an ace of spades. And once you take that first card out and you see that it's not the ace of spades, when you reach back in, the likelihood of drawing the ace of spades is actually just a little bit higher because now there's only 51 cards. This is dependent. And you'll notice the thing that I underlined here, without replacement. Pretty much anytime you see that, that means you're going to be working with dependent events. Because if you're doing this without replacement, then the probability does change. The probability of two events, of two independent events both happening is just given by this. You just multiply the likelihood of A times the likelihood of B. We just multiply those probabilities. Going back to what we've talked about before with connections to sets, A and B is referring to the intersection. And you might remember the intersection notation looks like that. A intersect B. In terms of Venn diagrams, the intersection is the overlap. So this little part right in here in between, that's the intersection. And that's what, that would be the probability of both A and B happening. Jessica grabs a random drink from the fridge and a random snack from the pantry. There's 10 drinks, 4 of them are sparkling water, and there's 8 snacks. 3 of them are applesauce. What's the probability that she gets both a sparkling water and an applesauce? So the first thing that I'm going to identify is what the question is, right? What is the probability? Okay, so I know I'm looking for a probability as an answer, and we want to get a sparkling water and an applesauce. Now, with this problem, notice that it's set up so that we're selecting from 2 different areas. We're selecting from the fridge and from the pantry. That means that whatever we pull from the fridge is not going to affect the likelihood of getting an applesauce from the pantry because they're separate. Whatever happens in one has no impact on the other. So we're going to use our formula, which is just the probability of A times the probability of B. And in this case, we want the probability of sparkling water. So I'll just write probability of water, and we're going to multiply that with the probability of applesauce. I'll just write apple. So notice that for the first one, we have 10 drinks and 4 of them are sparkling water. So the probability of getting a water is just going to be 4/10. For the second one, I see that we have 8 snacks and 3 of them are applesauce. So the probability of getting an applesauce is 3/8. Now you can reduce these if you want, and that's what I would encourage you to do, or you could just multiply them just like it is. For this one, I'm going to show you that we could multiply straight across and get 12/80ths, but that's probably not the best answer. It's not reduced. It is correct, but it's not reduced. Let's go ahead and work on reducing this a little bit. You could divide each of these by 4. I see that 4 is a common factor to both of them, and that would make then 3/20ths. And that's not going to reduce anymore at all. So we're done there. We can also use Desmos. Put this over here. So we could do 4/10ths, and I'm just using the divided by sign whenever I do this. It's not a special fraction sign. And then I'll do times 3/8. And then notice I get this decimal of 0.15. And that's correct as well because it is equivalent. But if I select this little button right next to the 0.15, then notice that changes to a fraction of 3/20ths. So this is how we can get reduced fractions using Desmos. William checks the weather app in the morning and finds there's an 80% chance of rain where he is. And later, William flips a coin to decide whether to study or relax. What's the probability that it's raining and he decides to study? Well, these two things definitely do not affect each other, right? Whether it rains or not has no bearing on how this coin is going to land. So what we're going to do is, once again, we're going to multiply the probability of A times the probability of B. Or in other words, the probability that it's going to rain times the probability that he's going to study. Well, the probability that it's going to rain, we can see that it's an 80% chance of rain. So there's really not a lot to do. I could just put 0.8 here. That's just fine. If you want, you could write that as 8/10ths, right? Maybe I'll come over here and do this. So 8/10ths. But 80% is just 0.8. And then we've got to multiply that with the likelihood that he studies. So it says he's going to flip a coin to decide whether to study or relax. So that means that if he flips a coin, he is going to have a 50% chance of it landing favorable to study. And then we just multiply those, 0.8 times 0.5. If we multiply those two numbers together, that will get us 0.40, or just 40%, or 0.4. If we were to do this with fractions, it would be 8/10ths times 1/2. And then I always like to reduce fractions and say I know that 2 goes into each of those. 2 divides into 2 one time, 2 divides into 8 4 times. And now when I multiply straight across the top, I get 4 on top and I get 10 on bottom. 4/10ths will reduce down to 2/5. So either of these answers would be appropriate. Next, we're going to look at conditional probability. Conditional probability occurs when two events A and B happen in succession, and the outcome of the first event is guaranteed, or it's given. And in fact, you'll often see the word given a lot. So for sure one of them happens, what's the likelihood that the next one happens? That's what conditional probability is referring to. So let's look at a few examples. The first one, consider the probability of drawing the 2 of hearts from a standard deck of cards. Well, the probability of drawing a 2 of hearts is just 1 out of 52. There's 52 cards in the deck, and only one of them is a heart. If you want, you can always pull up a screenshot of a deck of cards if you're not familiar with what's in them. I would absolutely encourage you to make sure you study what's in a deck of cards, though, because it will help with a lot of math problems involving probability. So now if you put that 2 of hearts back, like the probability of drawing that 2 of hearts was 1 out of 52, and if you put it back in the deck, consider the probability of drawing the queen of diamonds. Okay, if you put that first card back in the deck, Well, the probability of drawing a queen of diamonds is just 1 out of 52. Right? You have 52 cards in the deck, and there's only one queen of diamonds. But what if, what if you didn't put the two of hearts back in the deck before drawing a second card? Well, then the original sample space wouldn't be 52 cards anymore. It would be reduced down to 51. Because if you keep that two of hearts out of the deck, then you don't have that chance of drawing it. Right? We'll just get rid of it there. Now there's only 51 cards, so the likelihood of drawing a queen now is actually just 1 out of 51. That probability changed. So given that you drew a two of hearts and didn't replace it, what's the probability of drawing the queen of diamonds? 1 out of 51. The main idea behind conditional probability is that the outcome of one event changes the sample space, right? We went from having 52 cards in the deck to having 51 cards in the deck, and that's what changed. This notation is written with this vertical line right here. This is actually read as the probability of B given A. So the probability of B, that's this P part. So probability of B, and this vertical line right here is given A. Let's go ahead and look at how we can use this now with a couple other card problems. Two cards are drawn from a deck without replacement. Find the probability that the second card is red given that the first card was red. Well, let's go ahead and look at our deck of cards. I'm going to bring this down here so that just in case you're not familiar with the deck of cards, you still have access to that. The probability the second card is red given the first card is red. There's a few ways that we could write this, but I might even just write it like this. The probability of a red card given a red card. Okay, that's how you might think of this. Notice that this question is not saying, what's the probability of drawing two red cards? That is very different. This is saying, hey, you drew a red card first, right? That's what this part is. Given the first card is red, means that you took a red card out of the deck already. It doesn't matter what red card it is. I'm going to say it was the ace of diamonds. Maybe you drew that out of the deck already. What's the probability that the second card is red? Nothing to do with the first now. I don't like the first event happened. All I want to know is what's the probability the second card is red? Well, all I've got to do is look. I can see there's actually 51 cards left. And when I count how many red cards there are, I can see there's 13 hearts that are left, and there's actually 12 diamonds that are left in this case. So that's 25 cards. So 25 out of 51 is the probability that the second card is red, given that the first card was red. Again, that's different than saying what's the probability of drawing two red cards. I can't stress that enough. Let's go ahead and look at the next one here. What's the probability the second card is a face card given the first card was a 9? Okay, well, if the first card was a 9, I'm going to go ahead and just pick one of them and get rid of it. There. That 9 is gone. I already drew it. Okay, and so I could even say this. Find the probability of a face card given a 9. So we already drew the 9. Now, this is really just saying, from what's left, what's the probability that the second card is a face card? From what's left. If I count all of the face cards that I still have, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 face cards left, and there's 51 cards left. By the way, this is a weird one, but 51 is actually divisible by 3. So you can reduce a 3 out of the top and the bottom to get 4/17. That's a great question for Desmos as well. That's it. Okay, so make sure you watch out for this given, because it doesn't mean that you want two successive events to happen. It means something already happened. Now, what's the probability the second card is a face card? Okay. All right, let's go ahead and see how this given is going to impact when we start looking at tables and some probabilities and statistics. Here's uh, a chart that summarizes the age of the gender distribution of students who responded to a recent campus-wide survey. And the data is rounded to the nearest 10 students. That way we have a little bit nicer numbers. If one of these students is selected at random, find the probability that we get a male. Well, all we're going to do is look at the total number. There's 550 total, so that's going to be our bottom number. And then we just look for the number of males. There were 250 males out of the 550. So 250 out of 550. By the way, I would probably work on reducing that. If you want to use Desmos, you can. I know that 50 goes into both of those, and this is going to reduce down to be 5/11. But just in case, we'll go ahead and take 250 divided by 550. I get that crazy decimal. When I hit that fraction button on the right, it turns it into 5/11 for me. Next, part B says find the probability that we choose someone aged 18 to 24. So once again, we are going to put 550 on the bottom because it's out of all the people. We're not given that anything already happened, so nothing's going to change. But out of all the people, find the probability that someone 18 to 24 was chosen. Well, right here is our 18 to 24, and we can see that there were 250 of them that were chosen. So I'll put 250 on top. Once again, this is going to be 5/11, just like the last one. Part C, the probability of a male aged 18 to 24. Well, in total, there were 550 people selected, and all we've got to do is identify the males of that age group. There were 120 males, because if you didn't see that, all I'm looking for is here's the 18 to 24 group, here's the males, and where we overlap, that would be the 18 to 24 males, which of course is 120. So put our 120 on top, and then we can reduce that down, divide the top and the bottom by 10, and that will get us 12/55. The next one is where this is going to start to get a little bit more interesting. Notice we have this new notation now that we just learned, this vertical line, the word given. Says the probability of choosing someone aged 25 to 44 given that a female was chosen. So in other words, like you might be looking at this and I pull a name out of the hat and I say, hey, this is I chose a female. This is a girl. So what's the probability that they are of this age? The easiest way to do this on a chart like this is to either highlight what you want. Like if I'm only looking at the females, I could do this. But to be very honest, one of the things that I like to do is I just like to get rid of the things that I'm not allowed to use. If it's guaranteed that I've chosen a female and I'm only allowed to look at the females, then I can just get rid of the other ones. I'll get rid of those and I'll get rid of these. That way I don't accidentally use one of those numbers. Now, when I look at this, I'm going to say aged 25 to 44. That would be right in here. That's 100. So I know that 100 is my top number. The mistake that a lot of people make is they try to put 550 down on the bottom. But 550 is covered up. I can't use it. I'm not allowed to use it. It's already covered up this way. So it's actually 100 out of 300. That's because when it said given females, I'm only looking at these 300 females. So what's the probability that someone was 25 to 44? 100 out of 300, or 1/3. Next, it says find the probability of finding somebody that's old. Sorry for those of you that are 45 plus. Um, what's the probability that you choose someone old given you've chosen a male? So in this case, we're only allowed to look at the male numbers. These are the only ones we can look at, and I'm going to get rid of all the rest of this. I'll cover it up with my pencil or my paper. That way I don't accidentally use a number I'm not allowed to. As soon as I see this given sign, then that means I'm only looking at the males. These four numbers are the only numbers that I could possibly use on this problem. So the probability that someone's 45 years old, 40 out of the 250. So this will be 40 over 250. Next, I can divide the top and the bottom by 10 and get 4/25. You can do that on the calculator if you'd like. The last problem says male given they're on the younger side. Right? So let's get rid of all this. Notice this time we're only allowed to look at 18 to 24-year-olds. This is the only section that we can look at. Because it says given 18 to 24, meaning we for sure chose someone from this group. What's the likelihood we chose a male? What I'll do is I'll get rid of all the other numbers, cover them up so I don't accidentally use them. And now we say, given we chose someone from this category, what's the likelihood that we chose a male? Well, there were 120 males out of the 250 people that were that age. So this is just 120 out of 250. We'll divide the top and the bottom by 10 and get 12/25. I actually really like doing these conditional probabilities with charts because it's kind of fun to get to scratch things out. Not as much whenever you're on pencil and paper, but when you're on an iPad and you can just quickly erase things like this, it's kind of fun. Next, we've got some another chart, but this chart doesn't look like it's filled in all the way. Keisha made a two-way table showing the types of Crocs that she owns. Wow, she owns a lot of Crocs. Like, no judgment, she's just a collector. The table categorizes her Crocs by style and fit. Fill in the missing values based on the information provided. So this is kind of like a little game as well. This is a little like fill in the blank. What we have to do is first fill in all of these blanks, and then we can start answering questions. So let's look and try to find either a row or a column that only has one blank to it. The first one that I see is if I look at this row, I can see that there's 8 people or 8 of these with regular fit, 6 with sport fit, and 22 total. So I should be able to figure out what goes here just by doing some subtraction. When I add 8 and 6, that's already 14. And I know that I should have a total of 22. So if I subtract those two, I get 8, and that's how I can know that 8 goes right in there. Another one that I can do, any of them that, any column that only has one blank in it, right? That's where we're looking. So the next one that I'll look at is right here. I can see that there were 13 classic. I don't know how many were lined, but I do know that there were 22 total. So if I have 13 already and I need there to be a total of 22, I'll just do 22 minus 13 and get 9. So 9 is going to go right there. Now I have a total of 22. The next one that I'll look at is I'll go over here to regular fit. We could do this a couple different ways now, but probably the easiest way to do this is to say there's 8 total, and I already have 5 there. So 8 minus 5 makes 3 to belong in that spot. And then the last one for me to fill out would be the platform here. I don't know how many were classic, but I knew there were 7 lined. And so if I subtract that, if I go 8 minus 7, that'll get me 1. Now 1 plus 7 gets me 8. 5 plus 3 gets me 8. 4 plus 2 gets me 6. I'm just kind of double checking all these to make sure that they all work, and they do. We're good. We filled out this chart correctly. We can now work on answering some questions. What's the probability that a randomly selected pair of Keisha's Crocs are lined given that they are regular fit? So we are looking for the probability of lined given regular fit. So notice that if we are only allowed to look at the regular fit category, that would be these right here. And if you want, you can get rid of everything else. Like if you're comfortable, we don't need to do that. But you know what? Here on the video, I'm going to. So guaranteed, we are only looking at regular fit Crocs. So I can get rid of all the rest of these so I don't accidentally use one of the numbers. Oops. Knowing that I can only look here, this is a much easier problem. Find the probability that something is lined. Well, there were 3 lined, so I'll put 3 out of the total, which is 8. There we go, 3/8. That's it. I'm going to bring these back so that I can see them to do the rest. What's the probability that a randomly selected pair of Keisha's Crocs are sport given they are classic? Given classic. So find the probability of sport given that we're only looking at the classic Crocs. Okay, so only looking at classic, I'll kind of do this. I'll be like, there. And if you want, you can get rid of all the rest. We can only look at the numbers that are in that classic line now. We want sport given classic. So sport, I can see that there are 4 of them out of the 13. So that's where we get 4/13 from. There are 4 sport that we can still see out of the 13 total. Notice I'm not using the 22. It's covered up. I can't use it. If Keisha decides to wear a pair of platform Crocs, is she more likely to select classic or lined Crocs? And explain your reasoning. So this is a way of mixing math with life. Right here, it says she decides to wear a pair of platform Crocs. This is another way of saying that she's given platforms. Like she's made that decision. She is only going to look at the platform Crocs. Now, we can answer the question of, is she more likely to select classic or lined? Okay, so we can look at it a couple different ways. The probability of, let me write this out using a better notation. So we could say the probability of lined given platform. Remember, we're only looking at the platform ones, so that's inside here. Right, and we'll get rid of those. We'll get rid of those. We'll get rid of those. There. We can only look at those 8 total platform Crocs. And if we look at the lined, we can see there are 7/8. And if we look at the probability of classic given platform, well, I know that there's only one classic out of the 8 possible. 1/8. We probably wouldn't need to go this extent to identify the fact that she's much more likely to choose lined than classic. You could even just look at that and say, wow, there's 7 lined and only 1 classic of the platform shoes. So she's much more likely to choose lined. She has way more of them. Now, maybe this is, of course, removing the fact of which one she would prefer, whether it's classic or lined. We're just saying, like, if she were to just reach in to the platform section and randomly grab one, she's much more likely to choose a lined platform croc. Next, we're going to start looking at multiple events happening using the and notation. When events are dependent, the probability of both events occurring is still found by multiplying the chance of each event. The difference is the chance of the second event is affected by the outcome of the first. And then we're just going to be multiplying. Probability of A and B is probability of A times the probability of B given A. Remember, this vertical line right here means given that A happened, right? This is the same formula from earlier. If the events A and B are independent, then the probability of B given A is just the probability of B, right? If A doesn't affect B, then the probability of B is just B. 2 cards are drawn from a standard deck of cards without replacement. What's the probability that both cards are spades? Okay. Well, hopefully, if you know what's in a deck of cards, but if not, let me bring that back. So here's our deck of cards once again. You can see if we are looking with the probability that both cards are spades, what we're going to do is we're going to multiply the probability of getting a spade, and then we'll take that times the probability that the second card is a spade, given that you've already drawn a first card as a spade. Okay, don't get too confused by that. The probability that the first card is a spade, if you count them up, there's 13 spades and there's 52 cards. Then what's happening here is we're saying we are in fact drawing a spade. So I don't care which one it is, but let's just say that we drew the ace of spades. So if that one's gone, what's the probability that the next card you draw is a spade? Well, there's one less spade in the deck, and there's also one less card in the deck. So that's why both the top and the bottom number changed, because the number of spades went from 13 to 12, and the total number of cards in the sample space went from 52 down to 51. You can multiply these. Probably the easiest way to do this is going to be on your calculator. There's a lot of this that reduces down quite a bit. Like I know that 1352 is 1/4, and 12 out of 51 is 4/17, and this will just be 1/17. But I've done a lot of fraction work and played with a deck of cards quite a bit, so I know that. It's probably much easier to just go here to say 13 out of 52 and then times 12 out of 51 and then hit our fraction button and we still get 1/17. So go ahead and use your calculator. That's just good. The next one says 2 cards are drawn from a standard deck of cards without replacement. That's important. That means that the bottom number, I forgot to underline that before, these are dependent probabilities, and at the very least, that bottom number is probably going to change every single time. Okay. What's the probability that both cards are red kings? So the probability of a red king happening for our first draw, you can see there's actually only 2 of them. So this would be 2 out of 52 for the first card being a red king. And then we take that card out, we take one of them out. Notice there's only 1 red king left, and there's still 51 cards left. Okay. This will just be then we get that. That's scientific notation. It's kind of gross. I'll go ahead and write that as a fraction and say 1 out of 1326. And also just kind of reasoning through this, that should kind of make sense because the likelihood of drawing 2 red kings without replacement is not very good, right? When you reach into that deck, the likelihood of you just drawing 1 red king isn't very good, let alone when you take one of those kings out and then you have to reach back in and draw out a second one. This table shows the relationship between outdoor temperature and whether or not customers ordered iced coffee. Find the probability that a randomly selected customer ordered iced coffee given that the temperature was over 100. All right, well, this one, just like before, we really don't have to change what we were doing. Given the temperature was over 100, I'm going to start out by only looking at that, because when we see given, that means everything else doesn't matter. Cover those up, and this problem becomes much easier, I hope. Find the probability that a randomly selected customer ordered iced coffee. So we want the probability of iced given over 100. So we've already eliminated everything else, so we're only looking at the over 100, and now we look at the iced. So 96 out of, and again, some people still try to look at this number and they're like, oh, I just got to move that. Can I just move that to the side a little bit and just peek in over there? No, you can't do that. We crossed it out at the beginning for a reason. When it says given over 100, we know that we're only looking at these 140 possible orders. Okay. So this is 96 out of 140, and I'll use Desmos to clean this up. And we get 24/35. That's a reduced fraction. Find the probability that a randomly selected customer experienced a day over 100 and ordered an iced coffee. Notice that there is no word given, and nothing was implied that something was guaranteed to have happened. We actually want both of these events to happen. We want A and B to happen. And the really nice part about doing this in a chart is that if we look at all of the days over 100, so over 100, and then we look at iced coffees, we can see that there's this subset that is both. It's these 96 people. Those 96 people experienced a day over 100 and ordered iced coffee. And we can actually just say that this is going to be 96 out of 300. Next, I do want to show you how our formula works with this as well. So if we look at what our formula said, we can actually just multiply these two events, the probability of over 100 and the probability of iced coffee given over 100. So the probability that it's, this probability right here, iced coffee given over 100, that's actually what we got right here. So we can just take and put that down in this area here. So this would be 24/35. And the probability that it's over 100, that was 140 out of 300. So we can write that here as well, 140 over 300. And this is a little bit trickier to do, so we'll go ahead and go to our calculator on this. Let's grab calculator. We'll do 140 divided by 300 times 24 divided by 35. That does get us 32 or 8/25. And you might say, okay, that's nice and all, but how does that relate to 96/300? If I take 96 divided by 300, I also get 0.32 or 8/25. They're the same thing. So when you have a chart, it's just much easier to be able to see these. Um, we just went straight to this fact that it was 96 out of 300. But we can still use our formula to get there as well. All right, the last couple things for us to work on. Didn't mean to have that up. So a set connection back to what we did before. A or B is actually referring to the union. And when we add P of A and P of B, any overlap has to be subtracted. Just like when we did Venn diagrams, if we knew how many were in A and how many were in B and how many were in the overlap, we would always start in the overlap and then subtract to get the rest of the numbers. That's because those numbers in the middle got double counted. The probability of one event or the other happening is given by this. P of A or B is P of A plus P of B minus the overlap. Again, the reason that we're going to subtract the overlap is because these were double counted. They were counted twice. I'm going to kind of show you what that might even look like. On a six-sided die, find the probability of rolling the following: a 3 or an even number. So what we can do is we can say the probability of 3 or even will be the probability of a 3 plus the probability of an even minus the probability of even threes. Well, we know the probability of a 3 is 1/6. There's 6 sides on a die. If you want to write the sample space here, 1, 2, 3, 4, 5, 6, you can. And the probability of an even, we know that there's 1, 2, 3 evens. So that would be plus 3/6. And then we're going to subtract out the even threes. Well, there are no even threes, so this would be minus 0. That does get us 4/6 or 2/3. The probability of rolling a 3 or an even is 2/3. Next, let's do the probability of a 4 or an even. 4 or even will be the probability of a 4 plus the probability of an even minus the probability of an even 4. So the probability of a 4, that's just 1/6. The probability of an even is 3/6. Now the probability of an even 4. Well, that even 4, the probability of that one is 1/6. So it's just 1/6 plus 3/6 and then minus 1/6. That's going to be 3/6 or 1/2. For cases like this where it's very small, it's even just easier just to count them, and that's totally fine. But you should always kind of practice using the formula even on some easier examples. For example, here I could go through and highlight the even numbers, or sorry, highlight the 4. Whoops. I could also highlight all of the evens. And now everything that's highlighted is an even or a 4. And you can see there's 3 out of the 6 are highlighted. This would also work on the one before, a 3 or an even number. I could highlight the 3. I could highlight all of the evens. And now notice there's 4 of those numbers that are highlighted. So 4 out of 6. Using a standard deck of cards, what's the probability of drawing a king or a red card? So we'll do the probability of a king or red will be the probability of a king plus the probability of a red minus the red kings. The reason that we're subtracting the red kings is because the king of diamonds and the king of hearts gets counted here, and it gets counted here for the red cards. So the probability of a king, that's 4 out of 52. The probability of a red card, there's 26 red cards. But remember, the King of Hearts and the King of Diamonds got double counted. So that's why we're going to subtract them off. We're not getting rid of them. We're just taking care of the fact that they were counted twice, and we should have only counted them one time. So that will be 28 out of 52. And if you divide each of those by 4, that gets us 7/13. Using a standard deck of cards, what's the probability of not drawing a queen or a red card? Sorry, a queen or a club. There is a common mistake that's made in a problem like this, and that is that maybe people might think about, let's try to not draw a queen and not draw a club. And they'd say, well, there's 48 out of 52 not queens, and not clubs, there's 39 out of 52, and then we get rid of the queen of clubs, right? So the problem with this is we are way over 1. If you add all that up, you have more than 100% chance of that happening, right? You have a number that's bigger than 1. But remember that probability is always going to be between 0 and 1 inclusive, and this is definitely bigger than 1. So that's not the way to do it. What we are going to do is focus on this. Let's look at the probability of drawing a queen or a club. So the probability of a queen or club will be the probability of a queen plus the probability of a club, and then minus the probability of a queen of clubs. So the probability of a queen is 4 out of 52. There's 4 queens. The probability of a club is 13 out of 52. And then we have to subtract off the queen of clubs because the queen of clubs got counted. She got counted here in these 4, and she got counted here in those 13. That's why we subtract her off 1 time, because she was double counted. That's 16 out of 52. That does reduce down to be 4/13. Now, that's the probability of getting a queen or a club. This is where we have to now go one step further and take care of this not queen or club. And what we'll do there when we want to do not, that's the complement. And so we're going to do 1 minus 4/13 to get 9/13. There's a 9/13 probability of drawing not a queen or a club. All right, the last problem here. There's 40 people who exercise outdoors in a neighborhood park. Some exercise in the morning and others in the evening. Depending on the temperature, some people wear a sweater while exercising and others don't. This is a two-way table. It's a two-way table because it has 2 different variables. We have the clothing that they're wearing, and we're going to cross that with the time of day. That's why we call this a two-way table. One person is randomly selected from the group. Find the probability. All right. In order to do all this, though, we do need to go through and start filling in these numbers. The first one that I'll fill in is this one here, and that's because I know that there's 40 total and 17 were in the morning. So if that's true, I could just do 40 minus 17 to get 23 goes there. Next, I'll probably do this one here for the evening because there's 23 total in the evening, and I already know 20 of them did not wear a sweater. So I could take 23 minus 20 to find out there were 3 there. The next one that I'll do probably be this one. I know that there's 6 in the morning, 3 in the evening for 9 total. And this gets to be a little trivial here. If there were 9 sweater and 40 total, then there's 31. We just subtract those. And then the last one here, this would be 11. 6 plus 11 makes 17. Now that our table's all filled out, we can solve these probabilities. Find the probability that somebody exercised in the morning. Well, there were a total of 17 people in the morning out of our 40. Notice there is no given, there's no extra. We're actually just going to look here in the margins at the 17 and the 40. So that one is just 17/40. The morning and the sweater. This is another one where it's just easier if we look at the sweaters and we look at the mornings and we see where they intersect, we can see that they do intersect right here at this 6. There were 6 people that exercised in the morning and wore a sweater, and that's 6 out of 40. Again, there's no given in this case. It's just 6 out of 40. We could reduce that down to be 3/20ths for a little cleaner number. Next, we have morning or sweater. So we could do this a few ways. We can use our formula. The probability of the morning or sweater is the probability of the morning plus the probability of the sweater minus the morning sweaters. Okay. We can do that. And in fact, we can even do this with just the numbers of them as well. But let's go ahead and take a look at this. The probability that someone exercised in the morning was 17/40ths. The probability that somebody exercised with a sweater was 9/40ths. And then we have to subtract off the probability of morning sweaters. And the reason why we do that is because they got double counted, right? When we look at our mornings, right? That's those 17 out of 40 that we looked at. And when we look at our sweaters, we can see that those 6 people got double counted. So I'm going to subtract off 6/40ths here, because those 6 got counted here in the 9 and they got counted here in the 17. This does get us then, looks like it's 20/40ths or 1/2. Sorry for that small writing there. The next thing that you'll notice here with this problem is that we could even just go through and add up the individual categories. If we add up the numbers that are highlighted, not the total columns, but if we add up this 11, this 6, and this 3 right here, those are all people that were either exercising in the morning or were wearing a sweater. And if we add 11 plus 6 plus 3, notice that gets us 20 people out of the total of 40, which is still 1/2. So you can do these a couple different ways. Whatever way makes the most sense to you is probably just fine. Next, let's look at the probability that somebody was wearing a sweater. So the probability that somebody was wearing a sweater was 9/40ths. The probability that somebody was exercising in the morning, given they're wearing a sweater. So as soon as I see that given, I'm going to come through and I want to get rid of everything else that I don't want. Given a sweater means that we can only look at those individuals. And I'll get rid of those. And there. There. The probability that somebody exercised in the morning, given that they're wearing a sweater, is just going to be these 6 out of 9. Six out of 9 does reduce down to be 2/3. Next, it says the probability of a sweater given that they were exercising in the morning. Well, this time we're only going to focus on the people that were exercising in the morning. So if we only look at those, I'm going to get rid of those. That way we don't accidentally use some number from that category. Now, find the probability that someone's wearing a sweater if we can only look at the people that were exercising in the morning. That would be 6/17ths. And that's it. All right, well, I hope this helps out with some probabilities. Good luck.